All right, so welcome back. I hope you stretched and I hope you're feeling ready because we're going to go to chapter 3, which is the big O notation. This is the conceptually trickiest section of today, so I'm going to take things slow. Now, here's a question that sounds dumb, but isn't. Why don't we just time our code with a stopwatch? Stick a timer at the start of the code and stick a timer at the end. Then we just subtract. There's our answer, right? So why do we need this whole big O thing? Now, if someone says different computers run at different speeds, that's reason number one. Your gaming laptop versus a small old cell phone. That's 20 times the difference on the same code. Times are not portable. If someone says different inputs give different times, then reason number 3 on the list, same algorithm. Fast on 10 times, but dies at 10 million. Time tells you about one specific run, not about the algorithm. If someone says timing has noise, well, right. Reason number 4. Your laptop has Chrome and Spotify running. Each run gives you slightly different milliseconds. Timing has noise. An algorithm description should not. Here are the 4 reasons on the screen. Hardware varies, language varies, inputs vary, noise from other programs maybe. Stopwatches tell you about one specific run on one specific computer with one specific input, and we need something better. So, we need a language for describing algorithms that's independent of hardware, language, and noise. A language that asks, how much fundamental work is this algorithm doing? And that language is big O. Whoopsies, hit my mic. All right, next slide. The core idea in 3 words. Growth, not speed. Here's the entire idea of big O in one sentence. Big O measures how an algorithm scales as input gets bigger. It does not measure milliseconds, it describes a shape. It's like asking, how steep is this hill? Versus, how long does it take for me to climb? Different question, right? Different answer. Big O is the steepness of the question, about the algorithm's shape, not about your speed. Now, here's a bit of an interactive widget that I cooked up for you. It says, n equals 10, with the button labeled times 2 double. Below that is a table showing what happens at this value of n for 5 different complexities. I'm going to press double and we're going to watch what happens. So, n doubled from 10 to 20. Look at what happened to each row. O of 1 stayed at 1, which is flat. O of log n went from 3 to 4. Just one more step. O of n doubled 10 to 20. O of n squared went from 100 to 400. That's 4 times more work. Notice the difference here. I'm going to click double again for you. Let's look at it one more time. O of 1 is still 1. Log n, just one more step. Linear, doubled again. And quadratic, 1,600. It quadrupled again. My apologies. Now, let's make things a bit more interesting. Now that we're at 320, 2, 3. I click 3 more times, right? That's 320. So, look at the quadratic row. We have over 100,000 operations. The flat ones haven't moved much. The linear one is keeping up with n. The quadratic one is exploding. And that's what Big O is showing you. At small n, all these algorithms are fast, but as n grows, the shapes diverge. The fast ones barely move, the quadratic ones blow up, and the shape is everything. So, here's the rule of thumb to memorize. Imagine doubling your input. Ask yourself, how much more work? Same work? Then you're O of 1. One more step, log n. Twice the work, linear. 4 times the work, quadratic. Memorize that. Keep hitting my mic. So, let's see the named family of all these growth shapes. Here's the family of big O classes you'll meet in this degree. I'm going to read down the table, fastest to slowest. For each one, I'll give you a real-world example you'll actually encounter. Here's the O of 1 constant time. Same amount of work regardless of input. Example, reading an array index. It doesn't matter if the array has 10 or million elements, simply because going to array 5 and modifying it at index 5, it takes the same time because you already know where that index is, as we mentioned earlier in our class for arrays. Now, O of log n, logarithmic. It halves the work at each step. Here's an example, binary search, which we'll meet in 30 minutes in our next class. Also, reaching deep into a balance tree, looking up a word in a dictionary by flipping all the way to the middle and start to searching from there. Now here's another one, O of n linear. Work grows in proportion to input. Example, linear search. What we just learned earlier is a good example of linear search because, well, we covered linear search. Or summing all elements of an array, or maybe printing every contact in a list, which, if you notice, just adds another step. Now here is O of n log n. Linearismic. Slightly worse than linear, but much better than quadratic. This is the family of good sorting systems. Merge sort, quick sort, you don't need to write these yet. Just know they exist and know that they're considered fast. We have O of n squared, which is quadratic. 2 nested loops over the input. Here's an example, bubble sort, the slow sorting algorithm, or checking every pair of elements for duplicates. O of 2 to the n, this one, is exponential. It doubles with each input added. For example, you're trying out every possible combination of items or passwords, or, well, you're just trying to figure out because you're trying combinations. But you don't write exponential big O notations on purpose, simply because if you find yourself with an exponential code, that's a red flag that something is wrong in your system. So, here's the magic line in computer science. Write this down, okay? If you're taking notes again, write this down. Anything O of n log n or better is considered scalable in real-world systems. Anything O of n squared or worse will hit a wall on real-world data when you're handling all these big systems. That split is the most important intuition in this whole class. Now, let's see these shapes actually be placed on a chart, and you'll see exactly the line I'm talking about. Oopsies, chart's a bit broken. Let me fix it up for you guys. There you go. Here. All right. So, this is one of my favorite slides. It's interactive. You see a chart on the screen with 6 curves, one for each big O class. Below the chart is a slider for n, and a row of cards showing the exact operation counts for the current n. Watch. So, let's move. There's a slider here, but I made presets, so let's use that. At n equals 10, look at the cards. O of 1 remains a single operation. Log n, it remains at 4 operations. It moves up to 4 operations. Linear 10, operations. N log n, about 33 whole operations. Quadratic, a whopping 100 operations. They're all small, and they all look basically the same so far. See, this is what we're actually looking at. So there's not too much of a deviation unless you're working with O of 1, but some people are already struggling along the way. Now, moving on, let's add more data into this. This is where things get a bit more difficult. Now that n equals 100, O of 1 is still 1, log n is 7, linear is 100, n log n is 664, quadratic is 10,000. Now we're already getting some spread going on over here. Now, let's move on to 1,000 this time. N equals 1,000. Log n is 10. Linear is at 1,000. Quadratic, 1,000,000. Already 1,000 times more worse than linear, right? Let's move on to 100,000 this time. N equals 100,000. Log n is 17. Linear is 100,000. Quadratic is 10 billion, which is pretty crazy. So, watch the color change. It's flagged red as a danger zone. See that? We're actually moving towards the danger zone over here. But these are okay. 100k is still too much, but it's still fine so far. But this is the danger zone that we're looking at. But let's get a bit more dramatic. Let's multiply 100,000 by 10 and let's get 1 million this time around. 1 million. Log n is 20 operations. 20. Oof. Linear is 1 million. A modern computer handles that in about 1 millisecond, which is still pretty good. Still pretty good, but you don't want that in an actual system. But mind you, modern technology is such an amazing wonder. Quadratic is 1 trillion operations. A modern computer takes about 16 minutes of the same input size. Pretty crazy, right? Even the calculator broke. It just went to 1,000 billion, which should be displaying 1 trillion, but I didn't program that properly. Now, imagine you're an engineer. The spec says your code needs to handle 1 million users at the same time. Your prototype is O of n squared. What do you do? Now, some of you might be thinking, well, just buy a bigger computer. Well, that's the wrong answer, and a very common business answer. Hardware scales linearly. If your laptop takes 16 minutes, a server twice as fast takes 8 minutes, which is frankly still unusable. The shape of n squared is the problem, not the hardware. If someone says, use a different algorithm, that's it. Algorithm beats hardware almost every time. A better algorithm, say n log n, would run in about 20 million operations, which is 20 milliseconds, 3 orders of magnitude faster. And that's why big O matters. But here's a bit of a heads up. The log n curve looks almost flat. Students often think it's the same as O of 1, but mind you, it is not. It grows, just very slowly. At n equals 100, it's 7. At n equals 1 million, it's 20. Still growing, but just barely. Now that you can see the shapes, let's learn how to look at code and figure out which shape it has. Here's the simplest rule for analyzing code in Computer Science 101. Just count the loops. This will get you the right answer about 80% of the time. Okay, here's the method. 3 rules. If there's no loop, that's always going to be an O of 1 constant time. If there's one loop over n items, O of n, that's going to be linear. If there's 2 nested loops over n items, O of n squared, that's quadratic. Now, here's example 1. A method called first that just returns array 0. No loop, constant work, O of 1 again. Let's go to example 2. Here is the sum, which adds up all the elements, 1 for loop, n iterations, constant work inside, and that is O of n. And here is example 3, has duplicates. This has 2 nested loops, as you can see inside of the code. You can tell over here by the 4 and 4, they're both working with the array.length that we learned earlier in our class about arrays. Now, the inner one runs n times for each iteration of the outer. N times n is n squared. Therefore, O of n squared. Now here is example 4, sum twice. Example 4 is going to be a bit of a tricky one, but I'll do my best to explain it. So here's 2 loops, but don't you notice how these loops are? Unlike over here in example 3, these 2 loops are not nested. They're one after the other. Each runs n times. The total is 2n iterations. So, let me ask you all a question. What's the big O? Is it O of 2n or O of n? Now, if you answered O of 2n, close. But in big O, we drop constants. 2n is the same shape as n. It's still a straight line on the growth chart, just with a different slope. And we don't care about slope, we care about shape. So, O of n. Now, if you answered O of n, yes, you're right. Constants drop, 2n becomes n. The shape is still linear, twice the work, but still linear. So, two big rules to memorize from this slide is that nested loops multiply, one inside the other, n times n. Sequential loops, this is sequential, add one after the other, and plus n. After adding, you drop the constant, so sequential loops over the same array, still O of n. You're going to see things like O of 3n plus 7. We never leave them in that form, and here are the rules for simplifying big O. Now, 4 rules that we're going to be covering is Rule 1. Drop constants. O of 5n becomes O of n. O of 100 becomes O of 1. O of 3 times n squared becomes O of n squared. The constant multiplier just shifts the curve up or down. The shape stays the same. Now, rule number 2. Drop lower order terms. O of n squared plus n becomes O of n squared. At n equals 1 million, the n squared is 1 trillion. And the n is just 1 million. So the n is invisible. Drop it. And rule number 3, different variables stay. If you're iterating over 2 different inputs, both letters stay. O of the n plus m, O of the n times m. Neither dominates the other because they're simply independent from each other. Rule 4 is adjacent loops add and nested loops multiply. We just covered this in the last slide. 2 loops side by side, add, 1 loop inside another, multiply. If it's side by side, where they just stacked on each other, that's just adding. If the loop is inside of the loop, that's multiplying. Now, quick check. Simplify O of 3n squared plus 7n plus 100. I'm going to repeat that again. Simplify O of 3n squared plus 7n plus 100. We're simplifying this. Now, if you've answered O of n squared, perfect. Drop the 3 in front of n squared. It's a constant. Drop the 7n lower order term. Drop the 100, also lower order. Only n squared survives, therefore O of n squared. And if you say something else, well, the answer, as I said, is O of n squared. So, big O is intentionally imprecise. That's its strength. We're not trying to aim for total perfection right off the bat, because perfection, simply put it, is unrealistic, no matter how you look at it. I think over-engineering, over-complicating, and focusing too much on the perfect algorithm is going to hinder you from finding a real proper algorithm. You need to find what actually works when you're working with these real-world systems and what you can actually implement, because that's its strength. We're always trading precision for clarity. We throw away noise so the shape stays visible. Now, before we move on, let me kill a few myths some students bring in about big O. 4 myths that's likely going to show up on exams, so let's banish them now. I'll read each, then we'll talk about why it's wrong. Myth 1. Big O tells you how fast code runs in seconds. Wrong. Big O describes growth, not absolute speed. An O of n squared algorithm can actually be faster than an O of n algorithm on tiny inputs, but at scale, never. Myth 2. O of 2n is worse than O of n squared because 2 is bigger than 1n equals 1. Wrong direction. We always think about large n, not tiny n. At n equals 1000, 2n is 2000, n squared is 1 million, and n squared is 500 times worse. And myth 3, log n means natural log. Actually, in big O context, the base doesn't matter. Log base 2, log base 10, natural log, they all differ by a constant factor, which gets dropped. We just write log n and don't sweat the base. Myth 4 is big O is the same as the best case. Nope. Big O is what we call an upper bound. By convention, we use it for the worst case. There's a separate notation called omega for the best case, but it doesn't show up often in CS 101. When someone says this is O of n, they almost always mean the worst case of O of n. So, quick check on myth 2. Which is worse for large n? O of 2n or O of n squared? Now, if you guys don't know the answer, that's okay. Let's compute. At n equals 100, 2n is 200, n squared is 10,000. At n equals 1,000, 2n is 2,000, n squared is 1 million. N squared wins every time, eventually. So that's the whole lesson. Since n squared grows faster, that's the answer. It's always that, at every reasonable scale. So, now let's check if big O actually sticks and clicks with you. Okay, 6 quick check questions on the screen. Same drill as before. I'm gonna read it aloud, and you can pause the video and maybe take an answer. Then I'm gonna reveal it. So try not to cheat on this too much, because mind you, the only person you're cheating is yourself. All right. So question 1: What is big O of a single? What is the big O of a single for loop from 0 to n minus 1? Again. What is the big O of a single for loop from 0 to n minus 1? Okay, let's get on with the answer. The answer would be O of n. Because it's one loop, n iterations, constant work, pair iteration. But I won't be reading out why anymore, because it's always going to be on the screen, okay? Question 2. So, let's simplify O of 3n squared plus 7n plus 100. Again, simplify O of 3n squared plus 7n plus 100. You may write all of these down in a paper, or if you want to process it and pause the video again, but here. Okay, now I've given a bit of time. Let's move on with question 2. So the answer is O of n squared. We just did this on slide 24. Question 3. Which is faster on large input? O of n squared or O of n log n? Now, here's what's expected. N log n is faster. N grows slower than n itself, so multiplying by log n is gentler than multiplying by n. Now, question 4. What is the big O of the two adjacent non-nested loops over the same array? Again, what is the big O of two adjacent non-nested loops over the same array? Okay, let's give the answer. The answer is O of n. 2n becomes n. Adjacent loops add. Nested loops multiply. Keep note of this, okay? Question 5. What is the big O of array index 5? Now, here's what's expected. O of 1 constant. Constant time array access is what we're doing over here because we're simply calling for array index 5. We covered this on slide 6 for our videos on array. Now, question 6. If doubling n quadruples runtime, what's the big O? Okay, let's get on with it. The answer is O of n squared. Doubling input equates to 4 times the work. It's the signature of quadratic. That's how you can always tell when quadratic leaves its mark anywhere. And if you're struggling on question 6, let me stretch the answer a bit for you. Look at the algebra over here. If runtime is k times n squared, Doubling n gives k times 2n squared, which equals 4k n squared. So that's 4 times the original. So doubling input equates to quadrupling the work, equates to quadratic. Burn this pattern in your head if you're struggling identifying quadratic formulas. Okay? Doubling 4 times n squared. That's it. Doubling input, quadrupling work, that's quadratic, n squared. So now that you can describe how fast algorithms grow, it's time to learn fast algorithms that we've been promising. Binary search. But that's the entirety of our video on Big O. I'll be uploading the next video on binary search shortly, and you may be able to understand binary search better now that you have a good grasp of Big O.